In some situations, momentum must be conserved. This tends to happen when objects are moving freely, particularly in collisions. It's when two objects, they can both move freely. Momentum has to be conserved within the system. If it hits a wall or something like that, momentum is not conserved, so we can't use this then. But hopefully after a few of these examples, you'll be able to see when we can use the conservation of momentum. But typically when you've got two or more particles in the question, both of which can move freely. Okay, so we learned what momentum was in the previous video. And the conservation of momentum just means that momentum before the impact has to equal momentum after the impact or the event. So in this example here, we've got a rifle, which is currently stationary. It's got a mass of 3 kilograms. That's 3 kilograms without the bullet. Not that that's going to make much difference. The rifle is used to fire a bullet, which has got a mass of 25 grams. Given the bullet has a speed of 250 meters per second when the rifle is fired, calculate the speed of the rifle immediately after firing. Okay, so before firing, the momentum is 0. And that is because the rifle is stationary. Okay, so there's no velocity there. So we've got a stationary rifle. So that means the momentum after firing of the gun and the bullet combined must still be 0. This is why you end up with a little bit of kickback when you shoot a rifle. So after firing, we've got the momentum of the gun or the rifle and the momentum of the bullet. So we know that this has a mass of 0.025 and it's got a velocity of 250. We know this has a mass of 3 and it's got an unknown velocity. Now what we can gather from this already is that because the total momentum must be 0, the velocity must be negative. It must be moving to the left to counteract the momentum of the bullet to the right. You get a bit of kickback from shooting a rifle because the bullet has a lot of momentum because of its vast velocity. It's got a small mass, but it's got a high velocity. Okay, so we're going to have 250 multiplied by 0.025. That is the momentum of the bullet. So that's 6.25 Newton seconds to the right, according to my diagram, which means this must have the same momentum, but to the left. So if we're going to get that, then that means that 3v must equal minus 6.25, so that the sum of these two momentums is 0. That tells us that the velocity is going to be equal to, well, just over 2, isn't it? So if I divide that by 3, we're going to get 2.08. So negative 2.08 meters per second. Or if you like, 2.08 meters per second in the opposite direction of the bullet. Okay, then it doesn't matter which way my diagram is facing, because if my bullet went to the left, the gun would go to the right, and if the bullet went to the right, then the gun would go to the left. Okay, and that would be the speed of the rifle immediately after firing. Obviously, that would dissipate quite quickly because it's going to go into someone's shoulder or perhaps into some kind of support, but probably a shoulder at this kind of size of rifle. A second example. A car is travelling on a motorway. It has a speed of 70 miles an hour. It has a mass of 1,000 kilograms. The car goes into the back of a different car, which has a mass of 800 kilograms, and that one is travelling at 60 miles an hour. Calculate the speed of the two cars immediately after colliding. So what we're going to assume is that these two cars are going to come together and then they're going to move off as one object. So the first car has a mass of 1,000 and the second car has a mass of 800. What we do need to do is convert the miles an hour to meters per second. So to do that, we're going to take the 70 miles an hour there are let's go with 1,600 meters in a mile. So if I times that by 1,600, that'll give me how many meters there are. And then there are 3,600 seconds in an hour. So you divide that by 3,600, and that gives me 31.1 meters per second. And then I can do the same thing to the 60 miles an hour. It's going to be 26.7. And what I've done is I've rounded it to 3 sig fig for each of these, but in my actual calculation, I'm going to use the calculator answer, which I got here. I know it's not exactly 600 meters per mile, but we'll use that as an estimate for this video. Okay, and what's going to happen is these two cars are going to combine into one car. It's going to have a total mass of 1,800, or one object, I should say. And then it's got an unknown velocity. Now, the momentum before the impact, so the sum of these two momentums, that must equal the sum of the momentum after the impact, which is that momentum there. So what we can do is we can do, okay, so 70 times that number multiplied by 1,000. That's going to be the momentum of this car. And then plus 60 times 1,600 divided by 3,600, and then times that by 800. So that is the speed of the second car times it. That's mass. That's going to give me 52,444 Newton seconds. So that's the total momentum of the two cars before the impact. That must equal the same momentum directly after the impact. So to get the velocity, then I just need to divide that by 1,800, and I get 29 meters per second. Okay, that will again dissipate very quickly because there's a high amount of friction between the road and the tyres, but that is going to be the speed of the two cars coalesced immediately after the impact, according to the conservation of momentum. Okay, brilliant. Thanks for watching. My next video, we're going to have a look at kind of these situations in a bit more detail. What happens when they don't coalesce and become one object? What happens when they remain as two separate objects and they bounce off each other? You can imagine snooker balls on a table or something similar to that. Brilliant. Thanks for watching.